Next up, Roman Piffl, color index of digital meteors.
Hello, everybody. So we start with a few numbers. We have around 20 million number of single station meteors, around 10,000 number of acquired spectra, but 0 number of meteorites from meteor showers. So how do we recognize the meteor showers? When studying meteor showers, we try to get as much information as is possible. And it started with photographic research in the 60s, in the 20th century. And today we are witnessing an overflow of data from hundreds of stations around the world. With this data, we have good information about meteor showers, especially their dynamics and the movement of particles that make them up. Unfortunately, this data tell us a little about composition of these particles. Today, we obtain this information only from spectra, but which, however, only covers our area of larger particles. Although photometric data on recorded meteors give us an idea of their size, they say nothing about the composition of these particles. So, do we have any other options? Yes. Let's try using information about colors of meteors. Determination of color index. This discipline dates back to the golden age of visual observations of meteor showers. However, the definition of that index varies in different older works, and few works on its topics are not increasing much. I therefore decided to try the process to process colored meteors photographed over 15 years with my own camera, and the same camera and the same lens, using method I presented at IMO on Hungary 2 years ago. Here are some examples. Here is a cut of RGB channels. There is a color index for B and G, and color index for G and R for each pixel column. So it is some draconids, geminids, lyrids, Orionids. Did you see these meteors? Yeah? Okay. And these here Perseids. And here is an example of one picture downloaded from web. It is a large bolide. So what did I actually find out? The graph shows measured values of color index blue and green, and color index green and red. So we saw that here is some meteors from short periodic comets, Geminids and Jacobinids, or the Draconids. Here's Lyrids, Orionids, and here's the Perseids and Sporadics. So that is expected, but let's look back to the system I use. It is old Nikon from 1908. But important is that he has important spectral characteristics. It is the spectrum of meteors, it is some draconids, and here we saw that here is green, blue channel, green channel, and red channel. So we can use the red channel as sodium, green channel as magnesium, and blue channel as iron. And then we can construct a ternary diagram for these meteors. And this presentation is quite good. And this is interesting. We can say something, we can say something about quantitative composition of these photographed particles. So, but now a few limitations. The spectral sensitivity of camera is limited to the region from 40 to 70 nanometers. Above 70, it doesn't matter so much because there are some atmospheric lines, but below 400 nanometers, however, we have cut of the area where iron and calcium shine, and so we will not have the left part of covered in the ternary diagram. So here, yeah. Color images are greatly affected by extinction. At low values, at low altitudes above the horizon, it absorbs the blue component, so the meteors are redder than they actually are. Therefore, a detailed reduction must be made before the measurements. This, of course, also applies to the color transmission of the lens we used, and it needs to be measured also. Also problematic is interpret or filter out the green train, which is visible mainly in fast swarm of long period comets, for instance, Perseids, Lyrids, and Orionids, and I think that also from Leonids. We have no information about the speed and height because the meteor are taken from static camera. So this can only be obtained by parallel scanning the field with a video camera and matching the recording with another station. If we succeed, we can also extract temperature data from the color images, which would yield relatively complex data about the investigated particles. And last but not least, the sequential shooting with DSLR is demanding on the endurance of the mechanical parts, for instance, shutter. Yes? So it is better to use mirrorless cameras or dedicated color camera. So conclusions: photographic meteors with a color camera, photographing meteors with a color camera can bring a new kind of data about observed meteor showers. In one night, we can get dozens of color images of meteors, which is 1 to 2 orders of magnitude more than with the spectroscopy method. And it is enough to process them correctly. So finally, something for Peter. Thanks.
Thank you very much, Roman. That's really interesting. I got into meteors with DSLRs. I love photographing meteors with DSLRs. I love the way the pictures look, and it's nice to know there's some scientific value there too for single station observer. Are there any questions for Roman? Peter?
Thanks, Roman. Thank you very much. Coming back to the green train, I thought about that problem before you mentioned it on your own. You have in each streak image of the meteor, you have the superposition of the meteor head and also the green train that comes later. You can take anyone. I think most of them had a green train. And the green train is a phenomenon that is not strictly related to the brightness of the meteor head. So we should investigate this separately. And my question is, how do you subtract the green train if you just have the sum of both and you do not know which is which? How can you subtract that?
We only can measure red and blue channel, you know. So only here and here, yes, and green channel. And problem with green channel is that as we use color camera, we have a Bayer mask, you know, and we have two green pixels and only one red and one blue pixel. So if we delete green channel, the brightness of meteor will be not so good. And if you see, so it is the Orionis. Here, this is very weak Orionid, you know, and this. So this green part is.
Yeah, but the green of the green train has a different wavelength than the green of the, what was it, magnesium that you line that you have in the meteor. So it might be possible to, that's just a suggestion, take a narrowband filter of 557.7, I think, nanometer, and measure and photograph only the green train. And then you need a second camera of the same type and subtract that.
Not as simple as we use only one camera and so.
Use two.
Well, thanks a lot. Let's keep it on track. Thank you.